So far, we've only discussed reactions that are occurring at 298 Kelvin, which is 25 degrees Celsius. What happens to the change in entropy of the universe if we increase the temperature of the reaction to 50 degrees Celsius? And notice a little footnote here. When you work under non-standard conditions, we leave out that little zero in the superscript. So let's go back to our methanol reaction. And we had already found these numbers for the change in entropy, the standard entropy, and the standard enthalpy change. And we want to now find out, is the product favored or not at 50 degrees Celsius? To answer this question, we now have to calculate delta S surroundings at the elevated temperature of 273 plus 50 Celsius, because that'll give it to us in Kelvin, right? And then calculate the new value of change in entropy for the universe. And notice how we're leaving out that superscript O. There are two assumptions that we'll make as we do the calculation. First, the change in enthalpy for the system, that does not change unless we have a change in state. And second, the entropy change for the system does not change unless there is a change in state. So we're really saying the same thing for both of these guys. Step 2 in our methanol production at the elevated temperature of 50 degrees Celsius. From the previous slide, we know that the change in enthalpy and the change in entropy stay the same. How do we know that? Well, you got to look down here. We did a little research on Google, and we found out that the boiling point of methanol is 64.7 degrees Celsius. Therefore, there's no phase transition, and these two quantities stay absolutely the same. And the only thing that's going to change is what? Right over here. We have a new temperature, don't we? So we have to divide the delta H system by a new temperature, and we will get a new delta S surrounding. So that's the only difference. It comes in with the different temperature we're working at. So we will wrap this up now. At 50 degrees Celsius, our delta S universe will be a positive 64.5 joules per Kelvin. Earlier when we did it at standard conditions, we came up with plus 98 joules per Kelvin. Now what's the same between these two? Well, this guy's the same, okay? Now why did this change? Because we were at a different temperature, okay? So we divide it out, we get different numbers here. The reaction is still product favored. However, the magnitude of the change in entropy for the universe is reduced. That's important. For an exothermic reaction, as the reaction temperature increases, the reaction becomes less thermodynamically favorable. Increasing the temperature further will make the reaction non-spontaneous at some point. There's another way to look at that, and that's with this other thing called Gibbs free energy, which we will be getting to shortly. Let's work another example. We have ethane going to hydrogen gas and ethylene. And no, I didn't memorize that. I looked it up on the web. And we're giving you delta H naught for the system is 137.0 kilojoules. Delta S naught for the system is this. So your delta S surroundings is going to be delta H naught for the system, a negative, right? Remember that. You plug in the numbers, and you're given the temperature at 298 Kelvin, and you get minus 460 joules per Kelvin. How do you find delta S naught for the universe? Well, you add the surroundings to the system, and that's pretty straightforward. We say check for yourself, but let's go ahead and do that. Minus 460 and plus 121. And yep, that gives us negative 339 joules per coulomb. What if we increase the temperature of the reaction to 900 degrees Celsius or 1173 K? That will be on the next slide. Let's continue working this, and the first thing we're going to note is delta S for the system does not change because there is no phase change, right? We have gas here, gas here. Now your delta S surroundings will change. The delta H naught for the system does not change, okay? But we have a new temperature here, and that's the 1173 Kelvin. And we have the negative sign here to switch from system to surroundings. So delta S surroundings is different. Delta S system is the same, the 121. We subtract out this new delta S surroundings, and we get delta S for the universe. The change in entropy for the universe is 4.2 joules per Kelvin. So what has happened here? As the temperature increased, the reaction becomes product favored. This is important. For an endothermic reaction, as the temperature increases, the size of delta S surroundings is reduced. And again, here's an advertisement for Gibbs free energy that's coming up.